It never would have happened without Cooper trucks. One of the questions I get quite often when I'm teaching, because I teach electricity, is what exactly is voltage? Well, it's been taught forever that it's electrical pressure, and since all of you guys pretty much understand how pressure works, this should make pretty good sense. This is an electron. An electron is the negatively charged particle that spins around the outside of an atom, and it's what actually moves through a wire, and it's what actually makes electricity work. Electricity. Well, I like to think of these electrons as negative because they have a little negative attitude and a little negative charge. Maybe it works, maybe it doesn't for you. But it also helps to think about magnets, because everybody watching this understands what a magnet is and how it works. Okay, you take two magnets and you put the two north poles together, then they repel each other. Okay, everybody gets that. And the way it's taught in class is that like poles repel. However, we all know that if you take magnets and you put them together with the north and south pole together, or the south or north pole together, then they attract. There's a force that's actually pulling them together. And that force is the magnetic force. And we also teach that unlike poles attract. So like poles repel and unlike poles attract. So let's take our electrons, which both have negative charges, and we'll put them together, and they're fairly negative, as you can tell. I draw them that way because electrons are negative, and those look like some guys that got some pretty negative attitudes. Well, they have the same charge. And if you apply the magnet example, then what you get is you get a force that's trying to push these two guys apart. The force is pretty powerful. It's a pretty strong force. And it's what makes our components run, makes them work. So if you think about this, it works really well to just visualize a spring between the two electrons. Pretend they're billiard balls on a pool table. Well, you probably already have this figured out by now, because if you take two pool balls and put them on a table with a spring in between them and you let go, they're going to move because there's pressure in between them. All right, well, now they're a little more angry and a little more negative because they're being forced to be much closer to each other. And when you push these guys closer together, the force between them is pretty huge. And this is why it's called tension, electrical tension, high tension electricity. They're tense. They're stuck there next to each other, wanting nothing more than to get as far away from each other as possible. That's what makes them move. The spring is much more tightly compressed now. And if you carry this analogy to the end, the higher compression means higher voltage. So how does this work for us? Why is this theory important to us? It's important because voltage is what we measure, and knowing how voltage works helps when you measure it, so you'll know what it's doing or not doing. Well, if you put a bunch of these electron guys together, put them in a box, they call it a battery. So all these little electron guys in here all have negative charges, and they're all trying really hard to get pretty far away from each other. And that then puts them under pressure. This pressure is what makes everything happen. You can't have flow without a difference in pressure. Hydraulics or pneumatics, it doesn't matter. So if we take the battery and we connect the battery into a circuit, and by the way, it's called a circuit because it's a circle, you give them a place to go, they're going to go. They don't actually move at the speed of light, but the effect is felt at the speed of light. So with the switch open here, you're going to have charges to the left and charges to the right. The polarity is difficult to explain, but effectively, electricity is waiting at the switch. Sitting there stable, not moving. That's called static voltage. But as soon as you close the switch, now things start to happen. They start moving and moving and moving and moving and moving really, really fast. We put a motor in the way, and all of this movement works to create motion. So the motor goes zoom. And if a bunch of these guys in a box sitting there waiting to go is voltage, then it's pretty easy to understand what current is. It's them moving and getting away from each other. And we use that to do work. All right. Every load has resistance. Light bulbs, coils, resistors. And the resistance is measured in ohms. And the guy that figured this out, his name was George Simon Ohm. Hence the word. Now, for those of you who are like up on this stuff, yeah, motors do have back EMF, but we're going to cover that another day. We're just going to treat it as if it has ohms because effectively it does have ohms. All right, well, we get our motor there, and you ask yourself, what is the job of any resistor or of any resistance? What's its job? And the simplest way to understand it is that the job of the resistance is to keep the fuse from blowing. Oh yeah, by the way, then if it's a motor, then it turns. But the reason that the fuses don't blow when you turn things on is because the thing you're turning on has resistance. So how do we summarize this? Well, voltage, which is pressure, pushes amperage, which is current, through a resistance. This is actually Ohm's law, because Ohm's law is a concept. Ohm's law is a principle. Ohm's law is not a math equation. They use E equals IR and they teach it as math, but it is not a math problem. Ohm's law is a concept, not math. So voltage, which is pressure, resistance, and current work together to make our machines go.